Yesterday, just to continue. So, suppose we had a random variable d and there is a set of random variables x1 dot 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 say xq, and you consider the space spanned by them, you call that w as a span of this. Okay. What we did yesterday is, suppose you want to project d orthogonally in the space w. That means, you want to find out d cap as some c cap I xi, where c cap I is the best estimate. That is, if you really orthogonally project, the corresponding combiner coefficients are denoted by c cap I. So that the error between d and d cap, that is having minimum variance. Here in this space, the vector space of random variables, that the inner product was the correlation between random variables, norm was the variance, norm square was the variance and all that. So, if you take the difference between d and d cap, that error will have minimum variance and that error will be orthogonal with each of these x1 to xq, that is the correlation will be 0 and all that. Okay, that is what we found, that will give you the optimum coefficients. But the optimum coefficients will need the correlation values between x1 to xq and the cross correlation between external fellow d with each of x1 to xq. In fact, that optimal, if you really have c vector, c cap vector as c1 cap dot 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 cq cap, this was R inverse p, where R was E x, all are real. So, x x transpose, x is x1 dot dot xq and p is the cross correlation vector, right. This is what we know, this we know. Then I said that suppose we do not know the correlation value, so they change from time to time, so we have to make it adaptive. First step was to go for steepest descent that time. Okay, but steepest descent, exact steepest descent requires this gradient, and gradient it needs R and p. But something which I mean, in the beginning only I said, suppose I do not have that or they change with time. Then I went into the approximations, replace R by a wild estimate x into x transpose for a particular vector x. Similarly, p as just x into d, and I got into LMS algorithm, but I pay the price there. That convergence is not absolute, it is just a convergence in mean, and it will take a more time because as such it is a search technique, and that too it is a very approximate search technique. Then I said that the other approach will be what? That this error, if you call it epsilon square as E square, where this is d minus d cap square, this Ci caps were minimizing this, that is how they become optimal. Okay. Then the other approach was that let me find out an approximate value of these numerical value. How? I take data samples of d and also for each of the variables x1 to xq, and from these data vectors dn as, see, you can start at any point, I am starting at n equal to 0, dn, and for any xi n vector x1 xi0 dot 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 xi n. That is, I collected data at time equal to 0, collected data at time equal to 1, so on and so forth. Xi n, where I could be 1 to up to q, 1 to up to q. Okay. And you form the matrix x n as first column is x1 n, second column is x2 n. Though it is repetition, I need to rewrite this because I will be using this xq n extensively today. Then what I said, that if you minimize this, if you take this vector x n into a vector c n, where c n consists of some linear combiner coefficients, but since I am using data up to nth index, I am putting an index n, C1 to Cqn. So, xn into Cn means what? Linearly combining these columns by these coefficients, isn't it? So, if you take the span of the vector space span by these column vectors, then xn into Cn will be a linear combination of those basis vectors. So, some vector belonging to the column space of xn, we call it column space. Dn minus that is the error, and if you take the norm square of the error, that will be what? For each entry, for the first entry, take the error, square it up. For the second entry, take the error, square it up. Add all the, and all the terms. You remember how I defined the inner product yesterday, na? That I am now in vector space or n plus 1, where inner product x and y was x transpose y or y transpose x, which was same as x k y k. All are real, so no k0 to n. Okay, so variance is k0 to n x square k. That means x square 0, x square 1, x square 2, like that. Similarly, if I take the error, take this variance, that means this error at 0th index, square up. The error at 1th index, square up. So, add all of them. That is a net error. That if you divide by the total number of terms n plus 1, that will be a good estimate of epsilon square. If I minimize that quantity with respect to the C's, then effectively I will be minimizing this, because if this and this norm square, if I call it epsilon n square, you know this norm square means what? Take this error vector, take the 0th component, square up, take the first component, square up, take the second component, square up, add all of them. That is the norm square. That is the sum of the squares of each error, sum of square of error. But that will be, that of course divided by n plus 1 for averaging will be a very good estimate of epsilon square if I have got sufficient number of terms. So, if you take this to be very close to this, and minimizing this means almost minimizing this. So, the coefficients that we will get, they will be very close to the optimal ones. And in fact, in practice you really do not need up to infinite number of samples, just 100, 150 or 200, 250 is good enough. Whatever value you have for this, that is almost like epsilon square. And as a result, if you minimize that with respect to the coefficients, you minimize that, you will essentially get the optimal coefficients C caps. And that is why the convergence and all will be absolute and will be fast also. There is no search technique involved and all that, and it will be exact convergence. Okay. So, that means what I have to do? I have to project Dn orthogonally on the space, on the column space of this matrix, that is the space spanned by these columns. Okay. Find out the linear combiner coefficients. For n sufficiently large, they will be almost equal to these coefficients, because if you take this square and divide by n plus 1 and minimize, or do not divide by n plus 1 and minimize, in either case, because your minimization is with respect to the coefficients in this vector, you will get the same result. It is a quadratic function, isn't it? So, that is what we did yesterday. That is, we consider the space Wn, remember Wn span of, I already defined what is x1n, it starts at n equal to 0, x1 0, x1 1 dot 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 up to x1 n, n plus 1 length, dot 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 xqn. I want to find out this vector d cap n, estimate of d, which is the orthogonal projection of dn on this space. So, I can consider Pwn is the orthogonal projection operator for this space, that working on dn. That is what I want to find out as a linear combination of these elements. That is, as a this is what I want to find out, or equivalently xn cn. This is what you want to find out. Okay. Now, see one thing, suppose now at index n I was this, at this d cap n, is important to see this notation, d cap n, if I were to write it term wise, you should write like this, you will see very easily why very soon. D cap n 0, you have to have the subscript, d cap n 1, you will see very soon why I am, that is why I am doing this elaborately. Why? Because suppose you are now going in time index n plus 1, that is W n plus 1. This is at n, at index n, and now at index n plus 1. And obviously, at index n plus 1, my new coefficients will be not C I n, but I will be calling them C I n plus 1, because they will be obtained by taking data up to the index n plus 1. And obviously, there will be better estimate of the optical coefficients than C I n's, because I took some more data in the averaging process, isn't it? Say, as time progresses, they will be better and better. In that, there is no doubt, because you are doing better and better averaging. Epsilon n square will become a closer and still closer estimate of epsilon square as n becomes larger and still larger. As a result, these coefficients will be better and better estimate of the original optimal CIs, CI caps. Okay, that's fine. But suppose at index n plus 1, you want to do the same thing to obtain the better estimate CI cap, or sorry, CI n plus 1, say CI n plus 1. That means what you have to do, that time your this entire thing will be span of, all vectors are length n plus 2 now. And you want to find out d cap n plus 1 as P W n plus 1 d n plus 1. But you understand that this vector, even though its length is n plus 2 and this is length n plus 1, the 0th entry here will not be same as the 0th entry here. Please see this, this is crucial. First entry here will not be first entry here. How? Because here I took these columns from 0 to n, linearly combined, took the error, minimized that epsilon n square. I got some solution of C1 n to CQn, and then combine them, I got this. Next time my sum of square expression is different, because another term is coming. Last row having x1 n plus 1, x2 n plus 1, x2 n plus 1. So, total sum of square expression is different now, epsilon n plus 1 square, not epsilon n square. So, epsilon n plus 1 square if minimized with respect to the coefficients, you are likely to get new set of coefficients. If you combine these columns by the new set of coefficients, the resulting vector will be altogether different from what we had. You understand? That is why I am using this notation, this time it will be d cap n plus 1 0. Are you getting me? Please see that this is crucial, d cap n plus 1 1 dot 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 d cap n plus 1 n plus 1. So, this element, this is not equal to d cap n and the last entry. Is this clear? It is not that this part is same as this part, because the combiner coefficients have changed. Earlier you took this space, data was from 0 to n for every vector. You combine them, found the error, minimized the norm square of the error. Norm square of the error was called epsilon n square. You got one solution for the coefficients. Combine these columns by those coefficients, you get one particular d cap n. This. Next time you got a longer vectors, new data has come up. Again you combine with the new set of coefficients. Take the error norm square, call it epsilon n plus 1 square. Minimize it with respect to the coefficients. You are not mathematically, you are not guaranteed to get the same set of coefficients as before. It is a new epsilon n square 1 function, isn't it? One extra sum square term has come up, so overall has to be minimized. Okay. So, that means you get a new, in general you get a new set of coefficients. By that, if you combine them, naturally you will not get these elements in the first positions, first n plus 1 positions of this vector. You will get a totally new terms. Okay. Please understand this issue, because this is very important here in the development of this RLS algorithms and all. Another thing is, I will be always interested in finding out projection. Projection is like a filter output only at the current index. That means, for this vector, if by nth index is the current index, this component is of interest to me. At n plus 1th index, I got a better estimate in the form of d cap n plus 1, but the total vector is not required, because this is already passed. These indices are already passed. I cannot go back there. I am standing at index n plus 1. I want to find out that filter output at n plus 1th index only. So, my quantity of interest will be the last quantity always. Are you getting me? I am interested, please see the inner mechanism here. I am interested in finding out filter output. Filter output means combiner output. Strictly under filtering, because it is x1n, it is not xn vector, xn minus 1 vector and all that. x1n, x2n up to xqn. So, I am combining them, resulting vector I am calling combiner. But my combiner is giving me, I am trying to find out the combiner output at each index of time. At nth index, what the combiner is doing, optimum combiner, it is doing this projection operation firstly. It is theoretically what is happening, it is combining, linearly combining the columns, finding out the error, minimizing the norm square of the error. Norm square of the error is called epsilon n square, minimizing that. You are getting an optimal set. Putting that as a combiner, you are combining only the last entries of each vector and getting this guy, because that is my current index. This 0 to n minus 1th entry, no consequence now, because that is past. I am only interested in finding out the estimate at current index. Okay. Even though these terms are now better than they were earlier, because better combiner coefficients, more accurate combiner coefficients, more closer coefficients are more closer to the optimal ones have come up, and therefore, this would have been better. Okay, but still I am not bothered about, I am only bothered about the current one. Okay. I define a vector called pinning vector pi n 0 0 0 0 0 and only 1 n plus 1 into 1. When is pi n? N plus 1 into 1. That means I will be interested in these coefficients d cap n n, which is transpose n pi n. Very simple, the last element will be picked up, but this pi n is very important. See the structure of pi n, it has zeros and only 1. It just picks up the last guy. Have you understood this? That my resulting vector will be with a better coefficient, resulting vector will be the d cap n plus 1 will be a better estimate of d n. These ones will be giving a better, this fellow will be a better estimate of d0, this will be a better estimate of d1, because I got better value, better estimate of those combiner coefficients. They are more closer to the optimal ones than earlier. But I am always interested in finding out the combiner output at the current index only, because whatever past index cannot be revived anymore, isn't it? I am doing in real time. Okay.
So then to compute the C caps, don't we require the D vector, like the optimal C?
I need the D vector. So that is what we will do in the recursive business, that you will be given the C vector, C coefficients, C1n, C2n, dot dot CQn for nth index, and new set of data dn plus 1, x1 n plus 1, dot dot xqn plus 1. Using them by simple computation without doing all this elaborate computation, just simple recursive approach, you get me C1 n plus 1, C2 n plus 1. This is the entire business, and exactly without any error, without bringing any statistics, any E operator anywhere, just using algebra. Okay. That is the thing, that is the entire approach. And you understand this journey will take us to the optimal ones. C vector n, then C vector n plus 1, then C vector n plus 2. As more and more data are used in computing epsilon n square, it will be a better and better estimate of original epsilon square, and therefore, this coefficient sequence will march to finally the optimal ones, exactly, not in mean, unlike LMS. Okay, and no searching business, will march very fast. So, this is what it is. So, that means entire thing, you can say at index n, situation is like this. Suppose there is a thing x1n, you are multiplying by c1n dot 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 xqn multiplying by cqn adding dot 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 adding, what you are getting is the nth index data x1n xqn, what you are getting is this last fellow. And what coefficients? Coefficients obtained by using data up to nth index only. Those coefficients are called C1n, C2n, C3n, like that. Those have been put here. You understand? Please see this figure. This is the situation I am with, and this guy is the latest guy, d cap n n. This n indicates I have taken data up to nth index, based on that found out the combiner coefficients, then combining these terms using them at the current index n, getting this. This is the last guy. Then at n plus 1th index, these values change into the better estimate. That is the changing mechanism is the recursive least square algorithm we will be deriving. But what it will be doing then again? That time the new data will be x1 n plus 1. I am doing all this elaborately so that there is no confusion prevailing, you know. And I am using the latest, this C1, sorry, not C1, C1, and this is your this guy D cap. I have taken data up to n plus 1th index, based on then found out the coefficients and the current estimate, because I am combining the last elements of each of the vector by those coefficients, and I am getting these. So, this will be the mechanism. They will be updated, this coefficient updated by a recursive algorithm which will derive into this, but always they will be acting on the current data only. So, the current estimate, okay. Current estimate based on what? I have taken data up to nth index from the entire vector decoupling, then the last component. Here again I have taken data up to n plus 1, I have computed entire vector. So, those are also could be obtainable, better estimates of D0, better estimates of D1 than obtained here. But in practice I am not bothered about them, because I cannot be non-causal. So, I can only use the new set of combiner coefficients to work on the current set of data and get me this. This is the schematic, mind you. It will come in an indirect way, because I will be doing again linear prediction and all that, but basic philosophy is this. You understood the estimation mechanism here. Here it is more general. If it is a filter x1 n, there would be a delay here, then x2 n, there will be a delay here, x3 n dot dot dot, and finally a delay in this. Same here, then it becomes a FIR filter. Coefficients will be adapted by that recursive least square algorithm to the new set. Okay. So, you understood the philosophy involved here. I had to do this elaborately because it is not easy to conceive. Okay, and this pi n definition you do not forget, it is a pinning vector, it picks up the last guy. If it is pi n plus 1, it will go up to n plus 1, n plus 1, I mean n plus 2th position will be 1. Okay, there is one notion, I am just discussing various notions. Okay. Another thing which I was doing towards the end of yesterday's class, and I was just running through actually, so I had to redo that. That suppose I now want to, this I did to explain the framework, actually the basic dynamics or the mechanism of the estimation. Okay. But now so I want to find out for any particular index n only, I want to find out this coefficient Cn. What should be Cn, so that this error is, this vector is indeed the orthogonal projection, so that the error is having the minimum norm square in the usual, in the given norm square sense in this Rn plus 1 space, and therefore, that is orthogonal to each of these x1 n to xq n, again using the inner product for the R n plus 1 vector space. Okay. So, that was this, that if I do, I know that if I have E n vector, error vector, that was original D n vector minus x n matrix into C n vector. If you forget, this is x n matrix, isn't it? X1, this all these column vectors are present, you are multiplying by C n vector. So, these combiners are, these coefficients are linearly combining the columns, that is the projection. There is a projection, original error vector. Okay, you have to minimize the norm square of this error vector, isn't it? And that will give rise to, and that will, from that you will find out Cn, and that with those optimal Cn's, this error vector will be the, this will indeed be projection, this will be the projection error, and this error will be orthogonal to each component, each column of xn, because columns of xn are linearly combined, x1n, x2n up to xqn, right. So, that means if I do X transpose n E n. What is X transpose n E n? X transpose n means what was X n? X n was this, X 1 n, I am repeating here, X 2 n dot 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 X q n, that was your X n. Column, 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 okay. Now X transpose means just they become rows. This column will become row, so it will become X transpose n. Second column will become second row, X 2 transpose n. These pretty simple things, right? You can visualize it easily. First column becomes first row, second column becomes second row, last column becomes last row. So X transpose n times E n means this row times E n, that is the inner product between E n and X 1 n vector, that is 0 because E n is orthogonal to X 1 n. Then X 2 transpose n E n, that also is 0 because E n is orthogonal to X 2 n, dot 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 dot, isn't it? This will become 0 0 dot 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 0. But E n you substitute by this X n d n minus that means what is C n? Provided the inverse exists.
This is fast action.
Okay, provided this inverse exists. When does the inverse exist? Let us see this first. This is very important. First, look at this matrix X transpose X. This is a Hermitian matrix very easily, because if you take a transpose, you get this back. X transpose X again, Hermitian matrix. No conjugation here because I think nothing is complex. It is a Hermitian matrix. Further, it is a non-negative, not only Hermitian, it is a non-negative definite matrix as such, because any non-zero C, this C and this C are not same, or if you want, you can call A non-zero vector, any A transpose X transpose n X n A. This will always be non-negative. It is because X n A, if you call it B, after all it is a column vector, matrix into column, so column vector, then this is B transpose. This B transpose, isn't it? Take the transpose. So this is equal to, so this cannot be 0, which means a non-negative definite. But non-negative definite means Hermitian firstly, Hermitian means eigenvalues are all real. Non-negative definite means eigenvalues are not only real, they are greater than equal to 0. But if equal to 0, determinant will be 0. So non-invertible. But if it is positive definite, eigenvalues will be all positive. So this must be strictly greater than 0. This must be greater than 0. When will that be? Norm square is greater than 0 if the vector is non-zero, implies B must be non-zero. That is, you should not be able to find any A, non-zero A, so that X n A is a 0 vector. Please say this. Are you following me? This is norm square of B. This is always greater than equal to 0, but I want it to be greater than 0. Because if it is greater than 0, definitely I am guaranteed. You can say, why are you bothered about sufficient condition? If it is greater than 0, I will answer to that later also. But if it is greater than 0, I am through, because then all eigenvalues will be strictly greater than 0. Non-negative definite means greater than equal to 0. But if it is greater than 0, eigenvalues will be, that we have proved. For positive definite matrices, all eigenvalues are strictly positive. Then there is no problem. No eigenvalue is 0, determinant will be positive, or will be non-zero. In fact, will be positive. But this norm square greater than equal to 0 means, you know the definition of norm square. Norm square is always greater than equal to 0, and it is 0 only if the vector is 0 vector. That means, if it is greater than 0 means this B fellow should never be equal to 0 vector. Then obviously this will be greater than 0. That means you should not be able to find out any non-zero A, so that xn A is a 0 vector. Then you are guaranteed to have. Then the question comes, suppose I don't find. If it is true that I cannot find a non-zero A, so that xn A is a 0 vector, then it's fine, we are through. But that's like a sufficient condition. Are you following me? What I do here, xn into A must not be 0 vector. Then we are through. That is what I am saying. If it is not, if xn into A for non-zero A is not a 0 vector, then you are guaranteed to have this positive definiteness. So it is sufficient, but it is also necessary. Yeah, the other way, it is also necessary. That is, suppose it is not, that also we can see. Anyway, xn into A, what should be xn? So that for any non-zero A, you cannot find a non-zero A vector, so that xn A is a 0 vector. What is xn? Okay, fine. Hold on. These times a vector A1 dot 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 AQ, and not all the A1 to AQ is 0, because A is a non-zero vector, that is primary. Given for any such A where A is not a 0 vector, when can I say that this product will definitely be a non-zero vector? If the columns are linearly independent, then if you combine them, if you do this product means A1 times first column, A2 times second column, dot 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 plus AQ times last column, you equate that to 0 vector, then the only solution would be A1 to AQ 0, but that is ruled out. So that means, if you do not have that satisfied, that A1 to AQ you are do not allow to be 0 altogether, then if they are linearly independent, then linear combination cannot be a 0 vector. So that means this column should be linearly independent. So there should not be any linear relation between them. Can there be linear relation between them? See the difficulty in RLS. If suppose number of row here n is less than q, q is the number of columns. You have to start at n equal to 0, then equal to 1, then equal to 2, dot 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 dot. At some point only, at n equal to q only, you will cross q, then only you will go ahead, isn't it? Before you reach n equal to q, you have number of rows less than number of columns, dimension of the column space is, less than q. Suppose you are here, number of row is less than q, but dimension is what? Wherein dimension is n only, isn't it? You are looking length n plus 1 vector, so dimension is n. So n plus 1. Suppose n plus 1 is less than q. So you have got dimension of the space, vector space. You are taking the vectors of length n plus 1. Dimension is n plus 1, but that is less than q. So you have got more elements here than the dimension. So obviously that cannot be a linearly independent set. In a vector space of dimension say p, you cannot have p plus 1 linearly independent vectors. If you have p plus 1, there has to be a dependence relation, isn't it? Otherwise it violates the thing, na? This we have discussed at length. In a vector space of say dimension p, you cannot have p plus 1 or p plus 2 linearly independent vectors. You remember I did that beta in terms of gamma and gamma in terms of beta while proving the dimension thing. You remember, na, that alpha 1, then I construct alpha 2, then alpha 3, dot dot dot, and that process terminates at say n, and next time I start at beta, beta 1, beta 2 at m cannot be greater than n cannot be greater than, we have done it or not, isn't it? So that means if your number of row is less than q, obviously some columns will be expressible as a linear combination of the other. I can choose A1 to AQ accordingly, so that total matrix into that vector product is 0. Okay. You understand? And immediately what happens actually? If this product is 0, if it is non-zero, I have told you here, if it is non-zero, if they are linearly independent and A is non-zero, this is obviously non-zero, and then we are through. Question is, if it is 0, then what happens? You understand? Initially I wanted this, that let this B vector be non-zero vector. Question is, how can I ensure that? Given a non-zero A, then I worked out this elaborate matrix into vector. I said that if these columns are linearly independent, given a non-zero A vector, if they are linearly independent, then linear combiner, you are just combining them, cannot be 0, because if they are linearly independent, the only way the combined thing becomes 0 is by choosing this each A1 to AQ equal to 0, but that you are ruling out. That means the combined output cannot be 0. Okay. So, there I said that if they are linearly independent, I am through, because if this is non-zero vector, obviously norm of B square greater than 0, it is strictly positive definite, all eigenvalues are positive, I am through, determinant non-zero. Okay. So, then I am through, but if they are not linearly independent, and therefore, even with non-zero A, I can make this product 0, then am I a loser? That is a question. If it is not, if x into A vector, that is B vector is non-zero, I am a gainer. Understand the mathematics. If x into this vector, which is called B, if B is guaranteed to be non-zero, then I gain, because obviously norm square of B is greater than 0, positive definite, all eigenvalues positive, determinant non-zero. So, I am through, everything fine. But suppose on the other hand, they are not linearly independent, they are dependent, because of that phenomena that number of row is less than q plus 1, I mean less than q. Okay. And therefore, even with non-zero A, I get a 0 B vector. In that case, do I lose? Answer is I do, because if you can find out a non-zero A vector, so that this matrix times A is 0, no, because I am trying to see the case when B equal to 0. If they are dependent, then only it is possible. If this into A is 0, then my point is, then I am a definite loser. How? That is the question. If it is strictly not 0, like if they are linearly independent, combined, definitely it is not a 0 vector, because A is non-zero, and then if it is non-zero vector, this is total is B. If B is non-zero vector, suppose it is non-zero, obviously norm square of B is positive, positive definite, I am through, I am a definite gainer. On the other hand, if it is really 0, that is, if they are dependent, you can find out non-zero A, so that even if you multiply the 2, you get a 0 vector. Then what happens? Am I a definite loser? Answer is yes, because what is this my equation? This equation suggests that A vector is an eigenvector with 0 eigenvalue. Which means amongst various eigenvalues of this matrix, there is one with 0. So, I am a definite loser. So, this is not allowed. Are you understanding the mathematics, the mathematical logic? If it is strictly not equal to 0, fine, but is that really necessary? Question is, even if it is 0, can I still survive? Answer is no. The moment you equal to 0, it means eigenvalue is 0, one of the eigenvalue. Eigenvalue 0 means determinant 0. Okay. When you do maths, think like a mathematician, I mean use mathematician's logic. Okay. So, that means I now make the assumption that I am standing at an index n which is much higher, much larger than q. At that time I am doing all these things, and you can say that okay fine, if you want to do it recursively, you have to start at n equal to 0, n equal to 1, n equal to dot dot dot, n equal to q minus 5, n equal to q minus 4, n equal to q minus 6. What will do at that time recursively? That time number of row is less than number of column. I will do that, I will manage it somehow. That all those things will be built in our recursive algorithms, which you never dealt with in the LMS case, because we are doing pure linear algebra now, we will be doing. Okay. See these intricacies, huh? Fine. So, under that assumption, that is indeed a positive behaving matrix, that is I am standing at an index n which is higher than q, n plus 1 number of rows, n plus 1 should be at least equal to q or greater than q, n plus 1 equal to q means n should be q minus 1. So, I am standing at an index n which is either q minus 1 or higher, and there is no other linear relationship. Even if suppose number of row is much higher, you have to add that additional thing also, that there is no other relationship, linear relationship by some extra condition, extra equation linking the columns. Then of course, everything is finished, I cannot do anything. Okay. So, under that case, this is inverse, this inverse exists. This part, so what was our equation? We tried to find out Cn such that xn Cn dn minus that error norm square is minimized. Xn in general could be such that number of rows is much higher than number of columns. If dn is already present in the column space of xn, that is in the space spanned by the columns, then you will get a linear combiner so that xn into Cn exactly equal to dn and error is 0. Otherwise, if dn is outside the column space of this matrix, then you will get that combiner coefficient which will give minimum norm, minimum error norm. This matrix, this is a matrix working on dn, is called least squares inverse or more popularly pseudo inverse of the matrix xn. When this inverse does not exist, then they go one step ahead. They invoke something called SVD, singular value decomposition, and get this done. Okay, you will come across these terms in, I mean, if you have any further studies in communication control signal processing, you will come across SVD, beautiful architectures for SVD by the way, systolic arrays and all to compute pseudo inverse. So, you know, please see this pseudo inverse thing. What they need, all this RLS business I do, that suppose you have given me data up to dn, I have to find out this pseudo inverse, work on dn vector, get me this coefficient. Next time, these matrices have different, one more row has come up. So, new pseudo inverse would come up, you understand? It is very difficult to relate that new pseudo inverse to the original one, not so easily. The new pseudo inverse times the new dn vector will give you the new coefficient. There are recursive algorithms for pseudo inverse, this updating this matrix only. That you give me a matrix xn, found out a pseudo inverse. Now an extra row has come. How will the new pseudo inverse be obtained recursively? By some simple computation from the old pseudo inverse. Pseudo inverse updating. There are studies on that also in this RLS context. And then beautiful architectures for doing that. I am still on the periphery of RLS. I am trying to develop the motivation, develop insight, mind you. I have not started deriving things. I have not yet touched upon the RLS algorithm, how to derive algorithms. Okay. Anyway, one more thing. So, this equation I equated to 0, this equal to 0, and I had that Cn is equal to x transpose n dn. This is what I was doing yesterday. Suppose I divide this by 1 by n plus 1, this also by n plus 1. In that case, same Cn can also be written as like this, 1 by n plus 1 okay. What is this matrix? For large n, you can see easily x transpose n xn. X transpose n xn means x1 transpose n, x2 transpose n, this and then x1 transpose x1. You know this matrix multiplication. First element will be x1 into x1 divided by 1 by n plus 1. So, it will be an estimate of the variance of x1. Then x1 transpose x2n. It will be, you are multiplying the 2, averaging by n plus 1. So, it will be a correlation, good estimate of the correlation between x1 and x2, dot 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 between x1 and xq. Then again x2 transpose x1, x1 transpose x2, x2 transpose x1, they are same, divided by n plus 1, again will be a good estimate of the same correlation x1 and x2. So, this will give approach R matrix for large n. This fellow will approach P matrix, P vector easily, x transpose n dn. So, you see x1 transpose n dn means cross correlation between x1 and d. You are doing the averaging also, isn't it? So, you understand Cn tends to what? Finally, R inverse P, which is C cap for large n. Convergence is exact and absolute, no convergence in mean, and also no search technique, no approximate search technique, no approximation used anywhere, will be faster. One more thing, we found out Cn. So, what is d cap n? D cap n was xn into Cn, isn't it? By your formula, you are combining xn the columns by this, and Cn value we have already found out. The pseudo inverse thing comes here. This part is a matrix working on Dn. You call that matrix P something, that I'll complete the notation later, P Dn. It cannot be identity. D cap n, how do you find the identity? You are projecting Dn on subspace D cap n, how can it be identity? It is not identity. These are rectangular matrices. What is this? It takes any vector Dn, gives it projection on the space column space of Xn, okay, and it is a linear operator. If it is a matrix times a vector, this is a linear operator. Instead of Dn, if you have D1n plus D2n, P into D1 plus D2n means P D1n plus P D, it is a linear operator. This is the orthogonal projection operator that takes, this is a mathematical form of that orthogonal projection operator that takes a vector Dn. Earlier it was more abstract, now it has a specific form because I have got a very specific vector space structure, column vectors. Earlier it used to be just symbol, P operator and all that, no specific form, but I am now in a specific example of vector space, Rn plus 1. This is the orthogonal projection thing.
So, sir, if the matrix S is square, then it would be a identity matrix.
Okay. It will be
Identity matrix. If Xn is square.
okay. If X is square and there is no linear independence, yes, fine. So, but Xn is in general, n is increasing, na? Yeah. Okay. One more thing, I am forgetting the things. So, this much you have understood, orthogonal projection, pseudo inverse and all that. And also the Cn sequence will approach C cap very fast as you go from n to n plus 1 to n plus 2 and all that. Now, suppose up to index n equal to n naught, from n equal to 0 to some index n equal to n naught, system input statistics or Dn statistics, they are fine, they are constant. At n equal to n naught, suddenly there is a jump, the statistics changes, R value matrix changes, P vector changes. The point is, if you are immediately in the vicinity of n0, n naught plus 1, n naught plus 2, if you are standing around that zone, then what is the sum of square? You will be, suppose you are minimizing this, no, Dn, you are projecting on this Wn, isn't it? You are doing this, that's the problem. Okay, you are doing this projection. For that, what we are doing? You are combining this D0 minus Ci n xi 0 square, then d1 minus cin xi 1 square dot dot this is what you are minimizing. Suppose you are n is very close to n naught, just n naught plus 1, n naught plus 2, something like that. That time this sum of square will not be a good estimate of epsilon n square, because the statistics itself has changed, isn't it? Statistics has changed. Earlier, suppose input statistics were same, d was a random variable, x1, x2, xq were random variables. You are trying to find out those best C caps, C1 cap, C2 cap, dot dot dot. So you took several samples from the sum of square of error and minimize it. For large number of data, they will approach the optimal one. But suppose after some index, the statistics changes. Then what ideally I should do? I should try to discard in this summation contribution from index from 0 to n naught or n naught minus 1, and have more contribution from n naught plus 1, n naught plus 2, n naught plus 3, like that. At this part, then I will minimize with respect to the coefficients. I will get the new set of optimal filter ones, isn't it? But I cannot detect suddenly that this has happened at n naught. So I should have some mechanism to forget the remote past and concentrate it more on the current future. There are two approaches. One is called sliding window, where this sum of square you don't take. Here it is infinite window, as n increases, n can be 100, n can be 1 million, as it goes on with n. This growing window is called growing window. You understand this growing window? N equal to 0 you started, then n equal to 1. As time moves, the total number of terms goes on only increasing and increasing. It's called growing window. You can either make it sliding window, that may be from n equal to 0 to 100. You form a sum of square, minimize it. The next time n equal to 1 to 101. From the new sum of square, minimize it. So that way you are using a window only on a finite duration. Okay, so even if there is some change of statistics after sliding the window for a while, you will be able to ignore all the past and concentrate only on the current in the sum of square formation. That will lead to more complicated algorithms. There are algorithms. I will be considering what is called exponentially weighted growing window. This is a growing window, but exponentially weighted. I will be introducing a forgetting factor, a lambda real, lambda less than 1 greater than 0, but at the same time lambda very close to 1, like 0.99 something. And then I will have the inner product x y modified like this. Current term x n y n, then lambda times x n minus 1 y minus 1, then lambda square times x n minus 2 y n minus 2 dot 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 dot, lambda n times x 0 y 0. Okay, recent one multiply by 1, next one immediate past lambda, next to that lambda square. So since lambda is less than 1 but very close to 1, say 0.99, you understand this will be suppressed most, because lambda to the power n is becoming less and less. So only the current few ones will be more dominant. In this inner product, current few ones will be more dominant. This inner product, you can make it variance. So in the variance term also, only the current samples are more important, and it could be error variance. So in the error variance, if you find an error variance there, error variance will be more localized, more focused on the current error samples than the ones at n equal to 0, n equal to 1, n equal to 2. Okay. First, you verify that this indeed is an inner product. It will satisfy all the properties. You can also write it like x transpose, there are matrix, x is this, similarly for y, x transpose lambda n minus 1 dot 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 lambda 1 0 0 y. This entire thing, x transpose means x 0 to x n, y 0 to y n. So you understand, x 0 y 0 will be multiplied by lambda n, x 1 y 1 will be multiplied by lambda to the power n minus 1, simple, and added. This matrix is that lambda n. I will be using this and reformulate, rewrite those expressions of pseudo inverse and all using this tomorrow. Are you getting me here? If you use this in an inner product, say, and make it variance, and that to variance of the error, because after all, while computing the projection, you will be finding the error vector and minimize variance. In that variance, if you want to forget the contribution from remote past, n equal to 0, n equal to 1, and concentrate mostly on the current ones, then these weighting terms will take care of that. In the sum of square, dominating part will be coming more from current ones, x n, y n, or maybe lambda times x n minus 1, y n minus 1. If it is variance x n square, then lambda into x n minus 1 square, lambda square into x n minus 2 square, maybe few more terms, other terms will be sufficiently suppressed. Okay. So, lambda will be part of the algorithm. So, that is all for today. Thank you very much.